I want to introduce this weak acid strong base titration widget. It's inspired by the FET simulations. Let me just walk you through the panels and then demonstrate it. So on top is a species distribution. It shows how the weak acid gets turned into conjugate base pre equivalence point, and then we have excess of strong base after. And I'll talk a little bit more about that, how to interpret this. Then there's the pH curve, just classic, how much volume am I adding and what's the pH. I should say that this calculator is with volume change neglected. That doesn't change the position of the features, just, I mean, when they occur at which volume, but it shifts the pH a little bit towards neutral if you include the volume change. It's set up to have 0.1 molar sodium hydroxide and 0.1 molar weak acid in 100 milliliter. Here's the apparatus, the burette and the Erlenmeyer with the analyte has phenolphthalein in there, and it shows you what the pH is. So you could imagine there's a pH meter there, or you just watch the color change. And on the bottom I have some parameters you can change. The pKa is set to that of acetic acid right now. You can change the concentration. Technically that's an unknown, right? So that's why you're doing the titration. It shows you the current pH, when we expect the titration to reach the end point, what the pH is at the equivalence point. That tells you a little bit what kind of indicator would be useful. And then it says what the stage is. So right now it's pure weak acid because we haven't added any sodium hydroxide. This is pre-equilibrium, right? So this is what we have, and then of course it dissociates a little bit. Okay, so let's take a look at the species distribution. What do we mean by that? So this slide just shows what we have before any reaction happens. The analyte is a weak acid, AH, and the titrant is a strong base, which I just show as hydroxide, could be the sodium hydroxide. If I'm neglecting the reaction between the two, then I have a constant concentration of AH, neglecting volume changes again, and I'm increasing the concentration of OH minus. But in order to see what the major species is, we can just assume that for now, the weak acid reacts stoichiometrically or to completion with the strong base. So for every mole of OH minus that we put in there, we get a mole of A minus, so conjugate base in water. I'm not showing the water in this case. That works until this is used up, of course, right? And then we have this in excess. So if I merge these two triangles, then you can see our first approximation what the species are. So we're starting out with pure weak acid. Some of that weak acid gets transferred into conjugate base in the first stage of the titration until we reach the equivalence point. At that point, we have OH minus in excess, and so the weak acid will be mostly deprotonated state, almost 100%. If I run this to completion, then 100%, and then I get OH minus. We don't really know what the AH concentration is, so if it's a bit lower, I think, yes, then that equivalence point will occur earlier, and we'll have more excess of OH minus at the end of the titration if we always titrate to the same ridiculously large volume, right? Usually you would stop here, but we want to see how that progresses over the going all the way to twice the volume of the equivalence point. Okay, if I have more, then the equivalence point will be reached later. I need more OH minus to get there. And again, that's the whole point of the titration. And this is just for fun to see how the pH changes afterwards, but we could just stop there. Okay, that's how to interpret this diagram on the top of the panel. It's really about amounts, not concentrations, and then we don't have to care about volume increase doing the titration. We can just follow the amounts. And once the amount of OH minus added is equal to the initial amount of AH, we reach this equivalence point where the pH changes in a different way, as we'll see as we go through the simulation. Okay, the way this works is with the slider down here. So I can grab the slider. And as I said at the beginning, we have a weak acid. Students probably know how to calculate that. The pH is 2.88. I have a rule of thumb. It's approximately halfway between the pKa and the pH we would expect if this dissociated completely, which would be pH 1. So the mean between 1 and 4.75 is about 2.88. Okay, then we get into a region where we have both weak acid and conjugate base present. And so this is the buffer region. If I go to the half equivalence point, which is shown on top here, I guess I should say that there's a line that moves across here, and there's this dot that moves across here, and we can see where we're at. So I'm almost at half equivalence point. Here we go. The pH is equal to 4.75, which is the pK. Okay. As I titrate in more hydroxide, I have more and more conjugate base. I'm running out of weak acid at the equivalent point. In terms of stoichiometry, all the weak acid is gone. Or I could say at the equivalent points, we have exactly the same thing as if I had put in conjugate base. So if I make a solution with sodium acetate, that's exactly the same thing as making an acetic acid solution where I add the appropriate amount of sodium hydroxide. I get exactly the same composition. So here we have just conjugate base, which of course has an acid-base reaction and makes a little bit of HA and a little bit of hydroxide. This is why this pH is at 9.66 approximately. I'm actually over-titrated already, so I probably can't get this exactly to 100 because the stepper here is too small. But it tells me if I calculate it, I would expect 8.72. So I'm not neutral at the equivalence point, but I'm at 8.72. And again, I can do the same calculation. If this were a strong base at 0.1 molar, it would be pH 14, 13, and the middle between pH 13 and pH 4.75 is a good approximation of where we would be, and it's about 8.72. Okay, so we went through 3 phases already and stages, and they're actually shown here. We started out with weak acid, then we had buffer, then we have weak base. And now, from now on, going forward, we'll have a mixture of hydroxide, so strong base, and weak base. And the pH is dominated by the strong base because the weak base will not act as base anymore because it's too basic, the solution. The other thing that happens here is the change of color of the phenolphthalein. So we can see it starts getting pink here, and then magenta or whatever, that deep pink, hot pink. And now we're just increasing the OH minus concentration until we have supposedly 0.1 molar NaOH and 0.1 molar weak acid in there, plus the volume change that we're neglecting. I don't know if I paid attention to saying this, but you can see that the level and the Biot changes. This was written in collaboration with AI, and I let it do its thing. for some things and not correct it. So you can see hilariously the whole Erlenmeyer turns pink, so I guess it's filled to the max and is spilling out all the time. Not so realistic. Okay, I want to show you some other features. So I have the same calculator for a strong acid with a strong base. And I would point out that the second part of the curve looks the same, and that's because this is dominated by the OH minus. The first part doesn't have the buffer because with a strong acid, strong base, you just turn H plus into water. So this is all strong acid region here, and this is all strong base region. Okay, let's go back. Going to leave the slider here and play a little bit around with the pKa and the concentration of our analyte. So when I change the pKa, the buffer pH changes a little bit, and the weak acid pH and the conjugate base pH. So this point, and this curve. You can also see that we're running into problems with our estimated formulas being incorrect. So it's most visible if I go to higher pKa. So you can see my buffer estimate and my strong base estimate and my weak acid estimate don't really line up, so that we have this artifact here. So there's a couple problems here. At extremely low OH concentration, it makes a difference that there's also a conjugate base present, especially because the pKa is so high. So it does dissociate a little bit. So that pushes the pH a little bit up into the basic region here. And here Henderson-Hasselbalch is failing because we're actually, the assumptions of it that the concentrations don't change much, no longer true because we're actually making a lot of OH minus. The more experimentally relevant point is that if the pKa is like 8, it's going to be very hard to catch this equivalence point. You don't have a indicator that reliably shows you that you're at this pH. I assume you could just put it in the pH meter and theoretically say where you expect it to be and then stop there. But it's going to be a tough titration, and at pK of 9 there's hardly any transition, so that's you would switch to a reverse, a back titration probably to catch it on the other side. There's another glitch in here that is more subtle, and that's over here on the side of the at the beginning of the titration. So it starts at a pH of 2.02, and then as it switches to the buffer equation, it jumps down and then comes up again. So that's also a mistake. I could go ahead and fix that. So the exact solution, it's 2 linked equilibria with 4 parameters and 4 equations, and it comes out to be a cubic equation that you can solve. But I actually like this because we're using the buffer equation all the time, and so this is a very graphical way of showing that it breaks down. So I'm thinking that I should just keep it like this as a teaching moment. I want to get back to 4.75 if I can. Maybe I can't. There we go. Okay. So this was with a concentration that is exactly 0.1 molar. Usually you want to figure out that concentration. So here's a slider that we can see what happens if we're at 0.09. You will need less volume to get to this point where the pH shoots up. On the other hand, if it's 1.1, 0.11, then you take a little bit more of the volume. The graph on the top doesn't really reflect this correctly. So as I showed in the PowerPoint before, what really should happen is that this box should get smaller and bigger. But I didn't get that, and so this line is no longer a straight line. But you get the main point, which is that the equivalence point will be different if my analyte has a different concentration. Okay, so this was a walkthrough, the whole thing. Last thing I want to show again is these stages. So you start out with the pure weak acid, then you have the buffer stage, then you have the pure conjugate base, and then you have excess of NaOH. Thanks.